So what can I do with those? Well, no matter which word I'm hashing, it takes about the same time to create the hash. So it just takes, longer names are going to take longer to hash, but on average it's going to take a certain amount of time to make the hash, and it's fairly predictable. So I store these hashes for each of these names out here. Now the truth is I don't really need the name, but I'm going to leave that there for now. So the next thing I need to do is I left a little room over here for a index column. And so that's going to be number 1, 2, 3, 4, 5, and 6. So there's my index. Every row has an index for management purposes. This is used internally by the program to make sure that, for example, if I have 2 Bobs, do I have the right Bob? So if there's another Bob, some other Bob, he's number 7, I know that there's 2 different rows of data here. But we'll worry about that a little bit later. So, how am I going to use these hashes to facilitate my search? Well, first of all, I don't want to lose track of what I'm doing here. So I'm going to write some numbers here to keep track. Bob is number 4. I'll just write that here. Bob is number 4. Gary is number 2. Jan is number 5. Paul is number 6. Vera is number 1, and Zeke is number 3. And I will put my hashes next to those. So I'm going to make a little table of hashes and pointers to the particular data. So let's make a little table out here. So Bob's hash is 11. Gary's hash is 7. Jan's is 17. Paul is 6. Vera is 2. And Zeke is coincidence. Zeke is both a hash of 3 and a row of 3. So now we get rid of that. Now we have a hash table. How can that be used? So these are my hashes, and these are my index numbers. And let's say we're going to find Jan. So I take Jan. So basically the user types, I want to find Jan, J-A-N. The program has to say, okay, they typed in Jan. I have to hash that and find out what the hash for Jan is. So I run Jan through the hash and I come out to 17. So all I have to do is find 17, and so 17 goes to row 5, and there's Jan. So each of these is a pair of a hash and a row number. So Jan is number 17 again, so I type in Jan, hash it to 17, go down and find 17. 17 is row 5 is Jan. Great. Now let's look for Bob. Run Bob through the hash algorithm. That gives me a 11. So I go to the hash table, find 11, that's row 4, that's Bob. Okay, so all I have to do is take the name I want to find, run it through the hash, search the hash table for that hash, then that tells me what row to go to, and then I find the name. And that is fairly close to what I see people explaining how a hash table works. But do you see a problem here? Now I have to search the hash table. Well, in this case, the hash is only 1 byte of memory because it only takes 1 byte to hold these digits, but still I have to search the hash table. That's going to speed things up, but isn't there a better way to do it? And there is. And this, I have not been able to find anyone that explains it this way, but this is how I would implement a hash table. Instead of having a pair that has to be searched, I would build the hash table like this. Hopefully I can keep this straight. Now this is going to be a hash table with 100 possible numbers. So I'm going to have, let's draw a line here. I'm going to have row after row after row after row after row after row, and after row after row after row till I have finally 100 slots. So it's going to be a 100 slot hash table. And right now I only have 6 entities to go in there, so I'm going to have a lot of slack space, but as I add more and more people, this hash table is going to fill up. So let's go ahead and do this a slightly different way. So the hash for Vera is 2, so there's going to be number 0, 1, and I'm going to put that right there. And now it's the 3rd place, but when we count from 0 number 2 will be the third spot. So 0, 1, 2. So I put Vera's hash there, and then her row is number 1. Okay, now we're going to do Gary. Gary is number 7. 2, 3, 4, 5, 6, 7. And Gary's row is row number 2. Now we're going to do Zeke. Zeke is going to hash out to 3. So 0, 1, 2, 3. And it turns out that Zeke is row 3. Now we go to Bob. Turns out Bob is 11, 7, 8, 9, 10, 11. We're going to need some more space here. We'll just get rid of that. So number 11 goes to row 4. And now we have Jan. Jan is going to be 17, 11, 12, 13, 14, 15, 16, 17. 12, 13, 14, 15, 16, 17. And 17 goes to row 5. And last but not least, we have Paul, which is number 6. So 0, 1, 2, 3, 4, 5, 6. And that goes to Paul, which is row number 6. So here's the hash table as I would implement it. And perhaps a hash table could be implemented where you have to search the hashes. That would be quicker than searching the names, but this is instant. Watch what we do now. Because we know that somewhere in memory, this is going to be at a particular place in memory. Let's say it's at memory location. Oh, how about, just for an easy number, memory location 1000. Binary decimal doesn't matter. Now, what I'm going to do is I'm going to look for Jan, which is number 5. So I'm going to hash Jan. I'll do it over here. So Jan, when I hash Jan, I get 17. So now each one of these entries in this hash table that's only 100 entries long will take 2 bytes. 1 byte for the hash, 1 byte for the row, because we're not going to have any more than 100. That'd be our maximum number of entities. Now, of course, if we have more than 100 entries, we have to have more bytes in our hash table, but with only 100, 2 bytes for each entry. So to find number 17, all I have to do is take this 17, multiply it by 2, and that gives me 34, because this will be at location 1034. So in other words, this is going to be location 1000, 1001, 1002, 1003, 1004, 1006, and so on till we get to 1034 down here. So by using the hash table, let's look this over again. I hash the value, I get my number. Since each hash and pointer pair takes 2 bytes, I multiply that by 2. Gives me 34. Add that number to my address, points me straight to it. I don't have to search. I just hash, go, bang. And that doesn't matter how big this table is. If it was number 99, it's going to be hash it, multiply by 2, jump to it. So by using the hash table, I don't have to do any search. No searching. No searching through the database. No searching through the hash table. It's just right there. So that's how I would implement a hash table. Now our hash table is implemented this way. I can't find any information. Are hash tables implemented such that you have to search the hashes? I don't know. I can't find any information. But that's 2 possibilities, and this is the way I would do it. Now, there's a problem with this. Look at all the slack space. I only have 1, 2, 3, 4, 5, 6 entries. That means I have 94 empty slots. Well, of course, as I add more and more people to the database, that will start filling those up. But as these fill up, I'm going to run into a new problem. Let's go to number 7 here. Number 7 is going to be Dan. Okay, let's hash Dan. Let's hash him over here. Dan. We're going to hash him. Okay, this 65 throughout the 1, and we come out with 11. Okay, Dan's going to be number... Uh-oh. Dan hashed out to the same number as Bob. So I have what's called a hash collision. When two entities hash out to the same number, that's called a hash collision. Now, I have a problem to handle, and the chances of this happening, if I have 6 entities, I already have a 50-50 chance of having a hash collision. That may sound counterintuitive, but if I understand the math, that would be the case. And I did some hashing numbers to come up with this table to explain, and I did come up with an awful lot of collisions in trying to come up with these 6 names that were low numbers, so I didn't have to have 100 slots on the table and would not cause collisions. I had a lot of hash collisions trying to come up with these names, so it is very common. So 6 entities, I have a 50-50 chance of having a collision. So what do we do? Well, before I explain that, let me explain another problem. How about another Bob? So how many Bobs do I have here? 1, 2, how common is my name? Hundreds, depending on how many people are in the table. So I'm going to have to deal with 2 problems here, hash collisions and duplicate names. So how am I going to handle that? Well, one way to handle that is to have a hash table that's a certain size bigger than my database. That means I have a lot of empty slots that I can deal with. And I don't know the math. There's going to be somebody who's calculated the ideal size of the hash table compared to your data table to be able to handle this. I don't know the math behind that, but there's going to be some optimal size of hash table for a certain size of database, but you're still going to end up with empty slots. So one of the ways to handle a hash collision, and this is one I have found in my research that people say they do, although I'm not 100% sure that these people know what they're talking about, but the idea is that you find some way to use these empty slots. How would you do that? Well, there's probably all kinds of ways you could, like say, okay, if I hash and I have a collision with 11, let's just put the next one at number 10. Well, then what if something hashes out to number 10? Then you have a secondary collision. So I don't think that's a very good solution. But if you go back to my previous video, which I have linked in the description, about a practical data structure for database management, I talk about how to handle child databases where you don't know how many you will have. And that's the problem we have here. I don't know how many collisions I might have, and I don't know how many Bobs I might have. So what I need is yet another table.